Here we go. It's a muddy river. Something we're familiar with. We've seen it in creeks. We've seen it in the river. We've seen it in the Mississippi. We're all familiar with this. Right after a heavy rain, it looks like that for a couple days. What's going on? All right. This is what streams do. They work. They move earth and material uphill or from uphill to downhill. That's it. All right. They're the most important agents of erosion, okay? So the streams generally erode. They erode their channels. They lift loose particles up. They transport them down. They take little bits of sand and they use that almost like sandpaper against the side walls of a rock structure, the abrasion, grinding. They dissolve materials, whether that comes from the groundwater, has dissolved materials coming into the stream to carry dissolved materials downstream. They're moving all these things, these particles, downstream. All right. Streams transport sediment. All right. They can do it in solution, which is dissolved load. They can do it in suspension, right, which is the suspended load. They can do it scooting or rolling along the bottom, which is the bed load. We need an image here. Let's get this. Here we go. So the dissolved load is just little bitty particles. It's salt, it's calcium, it's other things that are dissolved in the water. So it's scale, it's line. It's things that aren't pure H2O. It's dissolved in there and it just moves from top to bottom. But it's taking material downstream. The suspended load is the mud. And it gets stirred up. And then sometimes it settles out. The suspended particles are ones that are literally, they're floating along and they move along with the stream. As the stream slows down, the bigger suspended particles start to sink out. As the stream speeds up, it picks more of those back up, and then you get big particles and little particles all floating downstream. Faster the stream's going, the more suspended load it's going to carry, the more bed load it's going to carry. The bed load starts and stops and starts and stops. It is the rocks on bottom. They're too big to really like pick up in the river and go consistently. Because as soon as the river slows even a little, it's going to settle back out and fall. But it rolls and it knocks into another one and it moves and it just moves up and down the stream on and off. That's the bed load. All right. Okay. We need, in a stream, you have two things we're going to look at: capacity and competence. Well, competence is what it can do. Can you lift big stones or just little pebbles? Can you move dirt, dust, and not dirt, dust? Can you move sand, silt, and clay in a suspended load? Or can you just move little bitty silt, right? What size piece can you move? That's competence. Capacity is just the total volume. Is it a wide, roaring river, or is it a little bitty trickle of a creek? That's capacity. Okay. Deposition. Deposition happens at the other end. Deposition is where you put things back down. We can look here. So headwater zone. This is more like last week. Transfer zone, deposition zone. Down here in this region, as the river really slows down, bigger and bigger things are going to start to fall out. And as they fall out, they build up mud, muck, and dirt. That's what a delta really is. It's the stuff that builds up because of this. So alluvium is the sorted, because it only slows down a little, only the big ones fall out, and then it slows down more, and then the medium ones fall out, and then it slows down more, and then the smallest ones fall out. Why is it slowing down? Because you're past the hill. You've lost all your velocities. If you roll a ball on a hill, it's going to roll, and it's going to roll down, and it's going to start rolling across the room, and then it's going to slow down and almost stop. So this is right before it stops. It stops when it hits the ocean here. The river isn't going to flow through the ocean. It's going to stop. And so as it slows down, you're depositing things out of the river, which means you build up a delta. There's a delta, right? That is a buildup of mud and sediment as you approach the sea, the ocean, the lake. Deltas look like the opposite of tributaries. In fact, they're not tributaries. They're what's my word here? We'll get to it in a minute. We'll get to our fancy word in a minute. They're distributaries. They distribute this all out. So as this river's slowing down, it's got to go downhill, but it's almost entirely flat. So some of the water goes this way, some of the water trickles this way, and it all just it divides. All right. This is the Mississippi River Delta from NASA, taken in 1976 and taken in 2001. Let's look at it in one image. 1976, this is the Mississippi in the main channel here. And you see shades of green and ocean. So if you take this at high tide, low tide, there's some shallow sand here to walk in. 25 years later, this is new land. You're filling all of this in. All right, this side, you've got look at that. That's built up sediment that came from, a long way, because the drainage basin of the Mississippi, we're going to talk about drainage basins, it's the entire land area that contributes water to a stream. Okay? So I may not have had the best. So the drainage basin we were just saying, the Mississippi, the largest in North America, anything here from the Continental Divide to the western side of the Appalachians even, all of this drains into the Mississippi River. Some of this down in southeast Texas, well, it just hits the Gulf directly. Same thing with this Alabama and Georgia. They go straight south to the Gulf. Anything on this side of the Appalachians will flow east. This side of the Rockies will flow west. The entire rest of this flows south into one river into the Gulf, which is why it has one of the largest discharges we looked at in the world last week. All right. Hold on. There's the delta picture. Okay. Natural levees. I'm not too worried about natural levees. They form parallel to a stream. So stream is doing its thing. There's a little bit of flooding. Wait, there we go. Where'd my image go? Wrong one. Well, I had an image up. We showed it for a split second. It's gone now. That's all right. We don't need that one. Natural levees, you got a floodplain. Nice big flat area. Water floods. When it goes out, it slows down, which means it drops that sediment, and the water recedes. Now that you've got sediment over here, do it again next year, and you're going to build up this area on the far side of the floodplain, and it's going to be a natural levee because it's where you keep depositing sediment from the small annual floods. Now, a real levee is run by the Army Corps of Engineers. Here it is. There's a lot to say about levees. There's a lot to say about the Riverwall and Cape. Good, bad, and ugly of them. What is the good? The Riverwall keeps downtown businesses dry, keeps them safe, keeps people at Cape, right? But the Cape side has the wall. The Illinois side floods. Illinois side's a huge floodplain. I know 93 is not the high water mark if you go downtown and look at the Riverwall. and look at the things up there. 93, the flood of 93 was a bigger deal than some of the other two that have topped it since, because it didn't just affect Cape Girardeau. It didn't just affect a small area of the Mississippi, north and south. It affected the entire upper Midwest. Iowa was horribly hit in 93. Okay, so was Minnesota. All right. It wasn't so much the Missouri River over here, but all the upper Midwest was hit hard by the flood of 93, and it lasted months and months. Just this slow build up of the river and crest and to come down. This wasn't one of those crazy flood, dump a lot of water up, 2 days later back down floods. Those are dangerous. Those are damaging. Those are not to be ignored. But the flood of 93 is a huge thing. Ask your relatives about it. See what they remember. The good, the bad, and the ugly of whether it's a levee or a flood control dam or something else, if someone builds one upstream, you better build one just as tall. And it becomes a race. Like, my levee's taller than your levee. If I build one on my side of the river, you've got to build one on your side of the river, or I flood you. Levees aren't perfect. They will fail. In fact, some of them are designed to fail. Recently, maybe 8 years ago, 7 years ago now, there's a spot near New Madrid that is designated a flood spillway, meaning that that levee was temporary. It wasn't supposed to be there. And in the event of flooding, it was designed to be removed to let the water out. Because letting the water out in one spot and flood an area reduces the water in the river for everybody downstream. Reduces the pressure upstream. It does good. It's natural. That's what the river would have done had we not put the levee there. Because they did build it. They had to blow it up. They used dynamite. They blew up the earthen dam and blew the levee, and flooded the farmland down there. I remember that specifically because there was a student whose family was farming down there, and he lost a textbook because it was at the family farm instead of at his house in Jackson for some reason. Whatever. The good, the bad, and the ugly levees, there's a lot to them. The Army Corps of Engineers is who maintains them. The water's got to go somewhere. And if somebody upstream builds a high levee, then it's just, we can't make this perfect concrete wall and make a drainage ditch from here to the Gulf. Not going to happen. Not going to be maintained. Not safe. Not right. Not realistic. So, all right. That's a lot about all the things. Rivers move lots of material. Guys, have a great day, and we'll keep learning.